Let's get started. So I promised, we're going to be doing induction today, but I promised that we'd have plenty of time to discuss syllabus, and I'll do this again next class. Uh, First of all, did anyone have trouble finding the website? Anything like this? In fact, I've even already posted recording from the first lecture, although usually I'll do it over the weekend, but we set up EdStem. Do people get invited or whatever? Know how that works? I've never used it, so I have no idea. Gradescope should also be set up. No questions? Fine by me. So, right. Okay. So last time was just our introductory lecture about someone we sort of laid out everything that goes on in this class. So just starting really basic logarithms versus exponentials, stuff in between. We did some recursion. Of course, I made a big deal about the recursive spec. We did our first divide and conquer algorithm with this merge sort algorithm. We analyzed it with recursion trees. We got our first practice was big O and big omega, at least in this class. And the algorithms were binary search, merge sort, and sorting lower bounds, which at least hopefully that part was new. I assume everyone else has seen the first two. So, right. This, for example, just to refresh your memory, was sort of like a complete answer for like if you're given a question like design and analyze an algorithm for sorting, right? You're making a recursive algorithm, so you got to put that sentence first, really declare what your input and output is, or else at some level, it's hard to verify your recursive algorithm is correct. The implementation is never too bad. Again, you don't have to write out all the, some reasonable high-level code is okay as long as it's completely unambiguous what the computer is doing, right? So I'm kind of writing out sentences here because I want it to be readable, but I think also it's clear I'm not cheating in any way. So just use your judgment, and then you prove correctness. For an algorithm like this, you're basically going to use your recursive spec as an inductive hypothesis, and you just want to show for every value of n, whatever you wrote down for your implementation will really satisfy that sentence. And the great thing is, when we go to that smaller problem of size n over 2, by induction, your algorithm is going to work there. Okay, so that's a very nice paradigm. We'll be doing that also next week as well, a lot of divide and conquer. Some level today, we're almost going to take half a step back and focus more on induction with a little bit less emphasis on algorithms. There'll still be some algorithms. And I know you've all done induction probably like 5 different times before. Nonetheless, I have found it, I've learned from experience not to skip this. So some of this you might have seen before. I think at least the last part will be new. I mean, a new something to prove by induction. So, okay, let me first explain induction, even though you've been explained to like a million times before. So, here's maybe an example to get us started. Okay, so let's say you wanted to explain to somebody how to climb up a long staircase. You want to give sort of an algorithm for it. How would you do it? You had to do it on the way here, so surely, yeah.
Like 1 foot up, then forward, and then foot up, and then forward, just aggressively.
Yeah, okay, so 1 foot. Okay, I think the key, yes, all right. So sort of what I have here, yeah, just, one step at a time. I don't know, you describe how to put your left foot up and then lift your body or whatever, right? Figure out one step. And then I think the key point, though, is that you know that you shouldn't have to re-describe everything in the same detail in the second, third, fourth, and fifth step. So, I mean, this is just one possible description, but I think, the key points are at the very beginning and end. We immediately recognize, at least in that description, that every step is identical. Okay, and we kind of recognize we just need to figure out how to describe one step. Okay, and then we can carry that on. And then at the end, you'll probably say something like, well, if you keep following these instructions, or recurse was a word that was used, you will get to the top. And the only question is, how do you kind of prove this? Okay. So I'll put proof in quotations because here we're not really proving anything like mathematically rigorous. It's a little vague, but it's just a teaching example. Oh, you're not supposed to see the celebration until the end. Oh well. Okay. All right. So something like this, right? What would be a base case in a quote unquote proof of this awkward thing? Yeah. No steps. In fact, I think that's better than I had. I had one step, but zero is even easier because then that's even less work. Okay. All right. So no steps. There's really nothing to do. Okay. I'm also going to take for granted in this exercise that our description for one step is just fine. Okay. So in the general case, n is bigger than, I'll fix that to 0. Okay. What might be the kind of what you kind of write down in a submission? Okay, maybe this is sort of awkwardly posed, but you might start with something like, uh, okay, let's assume or somehow justify that the instructions will work for one step. Okay. Then after that, n-1 steps remain, right? One step into a staircase, you have a staircase that's smaller ahead of you. And then by induction on the number of stairs, your steps will work for everything else. Okay, you're all super excited, but that'll work. Okay, what is the pedagogical point I want to make? I'm not sure. Okay, so maybe that's a very, very simple example. So example, you don't know why you're here. Here's maybe a slightly more complicated problem that will make, I think, induction and recursion much more helpful. Okay, first of all, has everyone already seen this puzzle before? Many of you have? Okay, so then you probably already know the answer, so that'll save some time. Okay, so this is an old problem, Towers of Hanoi, or maybe 100 years old. But there's some story, some myth. But the basic idea is that you have these 3 posts with big rings on them. Okay, and the rules, as you all know, is that one ring can only be on top of bigger rings. And your goal is to eventually get all the rings from here to here. Yeah. Okay, so since everyone has seen this, how do you solve then the Towers of Hanoi? Or maybe you've seen it, but you haven't solved it. I don't know. That's fine too. Okay, so first of all, it's not even obvious that's doable, but how do we go about solving this problem? Or if you want, you can just tell me where to move some rings around. We can walk through a few steps to get some sense. Yeah.
Just move one of the smaller ones to B next.
Okay, so we'll move this one, I guess, to B, something like this. And then I can move this one over here. And then what? Something like this. And then maybe I can go like here, maybe something like this. And okay, I guess this has to go here. Then this goes here, something like this. And this goes here. Okay, a little complicated. That was only to move the first 3. Now we got to, like, now what? Yeah. Okay, I can move the biggest one to C. Now what? B to A, B to C. Then A to C. Okay. B to A. I guess C to A. And B to C. Okay. A to B. A to C. B to C. I think we're still following the rules, right? Okay, we've only moved half the rings. And we're on the wrong post. Well, eventually we want to get to B. I guess now what would you do? And then, yeah.
Sounds to me like basically you can go from the ranks one at a time back onto the A. So there's C to B, and then
Okay.
and then B to T. Sorry, B ranks.
Okay.
And then C, A to C.
Uh, well, as a teacher, I'm not supposed to just get your point. I guess you go like this. Okay, this is getting awfully complicated. I'm only mildly sure we're making progress. Uh, something like this is what people probably have in mind. Okay. Oh, something like this. And you know what? In the back of my head, what I'm really worried about, at the very beginning, we chose to start moving from A to B, and I'm so worried that we should have chosen A to C. I have like kind of no idea, right? Okay. Um, okay. So one might imagine it's possible. I can imagine. I feel like I literally had toys as a kid that had 3 rings and you play around. Um, but in any case, we can appreciate that however simple the problem looks, the algorithm was starting to get really, really complex. You can kind of guide almost forced moves, although it wasn't clear what the right first move was. Uh, and we can kind of keep making progress. Yeah, it wasn't clear how long it was going to take. I think we had our fingers crossed that it would work. Okay. But at some level, I don't think we have a satisfactory solution in any case. So, does anyone want to give a more slick algorithm for solving the Towers of Hanoi problem? Yeah.
So I don't have an exact idea, but it feels as though if we have 3 posts with one being filled with rings, it's possible to take an arbitrary ring out of the first one, get any of those posts, given that other 2 are free, right? By moving the ones on top over and then moving it out and moving it back on top, right? And so by using that assumption, kind of, that given a set of 3 places with one being filled, we can take an arbitrary ring out, and for given right above it, we place on top of it in the initial starting point. If you, we can just repeat that on every single ring from the bottom to the top.
Okay. Uh, I think I get the vibe. But I think what we're kind of what's kind of going for, what we're hoping for, is something systematic, something that treats things uniformly, something that captures some symmetry. I think one of the things you were kind of observing is that, for example, if I kind of look like, sort of just above, I just look at the top 4 rings or something. I sort of have like a 4-ring Towers of Hanoi problem because these bottom rings, any of the 4 rings can go on top, right? It's as if it started there or something. So there is some symmetry. And so I think emotionally that's where we want to be. But now we got to figure out, I mean, I think this will happen a lot. You have this sense of an idea, and we just got to figure out how to get it down on paper sharply. A lot of it is actually just making it explicit. Yeah. Well, ultimately the rules are you can only move 1 ring at a time. But we're giving an algorithm, yeah.
We can do is if we need an odd number of rings, like let's say we want to make the range from A to C and we have an odd number of rings, we should move the first ring to C. And if we have an even number of rings, we should move the first ring to B.
Okay, so maybe there was a parity. Okay, so the suggestion is this question about where to move the first ring, whether it's C or B, it was kind of unclear. But I guess if you're paying attention very carefully, then you might have concluded that if there's an odd number of rings, you should probably move to C, you said?
If you want to move all the rings from A to B, then you should move an odd number to B.
Okay, so if it's an odd number of rings, we should go from A to B,
First ring from A to
the first one to B, and if it's even, the first one should go to C, and then that would work out. Okay, so that was possibly true. One has to rewind and think about it carefully. Okay, so maybe that's true. Still, can someone give me a really concise algorithm? I like concise algorithms. They're easier to grade. Yeah.
post I to post J, thinking about a third post K that you can use to build a locker. First, anyone with N rating. First, we have N minus 1 rings for post I to post A.
All right.
A lot of rings.
So here's an algorithm that's completely legal in an algorithms class. Okay, I'm going to move n minus 1 rings from A to C, and I'll move one ring from A to B, and then I'll move n minus 1 rings from C to B, which is exactly what you suggested. Okay, so here what we're going to do is we're going to use the power of induction. Say, okay, my goal is to move n rings, but I'm going to assume I know how to move n minus 1, and then you're just done. Okay, and you never have to worry about even these very clever parity observations, which actually probably could have unrolled into an algorithm, but clearly this is somewhat cleaner. So if we want to justify a recursive algorithm like this, then the first step is to set up our recursive spec to make it really clear what this subroutine that we have is. Okay, so I've given our algorithm a name, TOH, for Towers of Hanoi, but I've left open the parameters and I've left open the sentence. So who wants to give us some parameters? Who wants to give us a sentence? Yeah. Okay, n makes sense. What else? Yeah.
You think that we are like some bold objects that they're basically just a collection of rings on top of them. The rings itself all have kind of sides. You can check whether the moves are.
Okay, so first maybe A, B, C to enumerate our pools.
No, if you want to have more than 3 of them.
Oh, yeah, okay. Well, here we're just doing the 3 Towers of Hanoi. On your homework, you'll get like an infinite number of Towers of Hanoi variations to play around with. Yeah, after there's always n plus 1 Towers of Hanoi problems. So maybe those are our parameters. But what's our sentence? What are we trying to accomplish? We want to be clear about what we take in as input, and we want to be clear about the desired output, and then we have this contract for our subcalls. Yeah.
Given n rings that we can start with
Maybe. So I'll write sorted as something referring to the rules that they have to be in order and things like this. Moves all n or top n rings from A to B, subject to the rules of Towers of Hanoi. Okay. So we made very clear what we start with. Your input has n rings sitting on top of pollator in order. Okay. And they're sort of the n smallest. And you're just saying, okay, my goal is to move them all from A to B and still play by the rules. Somehow we've done little more than state the problem that we're originally tasked to solve. Yeah, it's almost exactly the original problem description. Okay. And that's often the case for recursive specification. All right, so we have a recursive specification like this. And now we just need to implement it. So who wants to implement our recursive algorithm? Yeah.
n minus 1. A, C, and B. The ring from A to B.
Yeah, so here it becomes clear why it's nice that we had A, B, and C in our parameters, because then we can change our targets and things like this. Okay, so there's an algorithm. Okay. One small bug. This is clearly the main part of the algorithm, but there's one thing missing. Yeah. Yeah, so what should I write to address the base case? A little louder? Okay, so we don't have to do anything if n is 0, so maybe I'll write if n is bigger than 0, then we'll do those steps, otherwise it's just done. Okay? So at some level, it's a very simple algorithm. And if we reconstruct a solution, our recursive spec was roughly just restating the problem. Okay, and then realizing, okay, you go down, and then you have this very powerful subroutine. And then you avoid this whole complication of trying to figure out which spring goes where and all this kind of thing. You know? Any questions? I think if we played this out, this would have taken a very long time. Do we want to look at the running time of this? So we had 8 before, right? And even 4 was taken forever. So I think we have something like t of n is equal to 2, t of n minus 1 plus 1, right? And if you start unrolling this, you're going to get 4 t of n minus 2 plus 3. This is because each of those tn minus 1s will give you plus 1, and then double into 2 more recursive calls. And then you're going to get 8 t of n minus 3 plus, it'll be plus 7, but that's really coming from 1 plus 2 plus 4, right? So you can start imagining, okay, you're getting 1 plus 2 plus 4 plus all the way up to 2 to the n. Yeah, so it would have taken a very long time. Okay. All right, so how do we prove correctness for something like this? Yeah. Proof by induction. Fantastic. What would be the parameter we're doing induction on? N. It's the only parameter. Okay, so what should I write first after I write proof by induction? Sorry? Oh yeah, I suppose you could. So I'm going to say, I don't want to write it all out. I'm going to prove that our algorithm implements that spec we wrote above for all values of n. That would be the full sentence written out or something. All right, then what? Base case, what would be a base case? So base case n equals 0. This is obviously okay. There's nothing to move. The algorithm doesn't do anything. And then if n is bigger than 0, what should we write? Yeah, so, or you can assume, I guess, yeah, so we know it works for, say, n minus 1 by induction. So, you could say something like, this step works by induction. It does what it's supposed to. I'm not going to write it out in full. And then this step is a legal step because you're moving to an empty post, one big one to the next. You're not violating any rules. And then your last step is also going to be okay by induction. Okay. So not too much to it. But the key point is that our recursive calls are correct by induction. And if you assume those two are correct, then it's not so hard to justify the whole algorithm put together will be correct. So this induction hypothesis does a massive amount of lifting for you. It does a ton of lifting in terms of we don't even have to be aware about this parity trick or anything, right? It just sorts out everything for you. It does all the work algorithmically and basically does all the work in terms of the proof of correctness. All right, yeah.
base case would have to be like n equals 1. Like we can prove correctly at our height 1. It's like, I guess being we have no disks at all doesn't necessarily help us by like doing induction. So at least looking at this, I'm not intuitively sure that we can move n-1 rings somewhere else if only our base case is if there are no rings, we don't do anything.
Okay, so n equals 1 versus n equals 0. So let's parse this then, since this is the one that's disturbing. So n equals 0, at least that's correct, or you're okay with that, right? And you're only worried about n equals 1 because we didn't do it explicitly. Okay, so let's look at what happens for n equals 1. Our algorithm would move 0 rings from A to C, and we know it does 0 rings correctly. And then it'll move 1 ring from A to B, and we know that follows the rules. And then it'll move 0 rings from C to B, which we know it does correctly by induction. So we can just, 1 will be the first thing that's proven by induction, and that's okay. If you wanted to do 1 because you're more comfortable with it, that would also be fine. That's not a big deal. Yeah. Yeah.
Complete argument, we also need to say that in step C, that we know that the n ring is larger than n minus 1 ring.
Yeah, so the full sentence is, I mean, there's a few paragraphs written in notes. So I think a full sentence you might want to set up something like, okay, so if I look at the top n minus 1 rings, they give you an n minus 1 ring Tower of Hanoi problem because that nth ring is bigger than everything else. So if I ignored it, I have a clean n minus 1 ring problem, and that would, so yeah, you can put a little bit more discussion around why, the input is, you really have an n minus 1 ring problem. So it is probably worth mentioning that, you're only touching the n minus 1 top ring. So the bigger rings down the bottom, they kind of play no role. You're really looking at n minus 1 ring problems. Yeah. Yeah.
Is it necessary? Is it necessary to have that third variable?
Is it necessary? Well, I guess it's a little subjective. To me, I think it's just easier to have C in there. It plays a role in the algorithm. Otherwise, I don't know, you might want to change. Okay, it is true that it doesn't appear correct quite in our sentence. It does appear in our algorithm. Otherwise, you might have like the first line of your algorithm be like, let C be the third post that's not A or B or something. So maybe either way, but yeah. All right, anything else? Yeah.
But typically, it makes sense that this ends up working. Like when you get to step where you actually move the biggest one that you're currently considering over to B, for sure there's not going to be something if you like B to whatever you're right? So like, how would you prove that it's going to be empty?
So here I think the previous step tells you that you've moved the top n minus 1 rings from A to C. So you know the top n minus 1 rings are on C, and in particular not on B and not on A.
So you're saying it works because for soon it works. Like, I don't know.
Well, okay. I guess it's good, quote unquote writing proofs are going to be a little bit touch and go until we get a little bit more used to it. But I think here I feel very comfortable saying, you start with n rings on post A. By induction, that routine is going to move the top n minus 1 from A to C. And there, I think if I said something like, at this point, the nth ring is at the top of post A, none of the rings are on post B, and the remaining n minus 1 rings are on post C, I think you can just say that and you don't need to like somehow prove it. That's sort of implied by the previous statements. And probably like the first few homeworks are going to be a little awkward because sometimes you'll feel like you write too much and sometimes you won't write enough and we'll be like, we're looking for more here. And you'll be like, well, what the hell? Last week I wrote too much and they said I wrote too much. And we're just going to go back and forth. Yeah, like an unhappy family, but it's going to be okay. And eventually you'll build some taste. At some level, you might also be thinking proofs as well. I'm trying to get a certain score on my homework, right? Did I check off the boxes? But in the long run, you're writing these proofs for yourself, right? these might be relatively simple problems. You're not really so worried about them being correct. But you really want to go into a new problem, right? Where you can't just look up Wikipedia. And you're trying to do something new. And then you really want to formulate something new as a recursive spec. And you want to convince yourself it's correct. You don't want to ship something into the wild and be like, you know. So at some level, the proof eventually will be to your own satisfaction, but it might take, a full semester to develop some taste in this regard. And yeah, it'll be the usual back and forth. We'll figure it out. Okay, good. Anything else? All right, so let me take it up one small notch. So before the goal was just to move all the rings over, following the rules. It wasn't even obvious that was possible. Apparently it is. Now I'm asking you to do it with the minimum possible number of moves. So first it was a miracle just to be able to describe an algorithm. Now I want to kind of do the optimum algorithm. Okay, is the distinction okay? So before we're just trying to get the rings over from A to B. Now I want to go from A to B with the minimum total number of ring moves. Yeah, it's about as much as I can ask for within this problem, I think. All right, any ideas? Yeah. Can we just assume that we just made the optimal move? Can we? Anyone want to fill in? Can we assume, or how would we assume, or would we justify assuming that we're making a minimum number? Yeah.
Solution would be the minimum number of moves, so you have to calculate the number of moves previous tell, right?
Yes.
So yeah, I guess I don't know. If you have that's
Yeah, I think you're all sensing it. Just how do we put a finger on it? Yeah.
for one ring, where is the optimum measurement to be?
Okay, so one ring we know how to do optimally. 0 rings too, I think.
So then apply that recursion.
Okay, if we want to do it recursively, then how would I really do that? Down on paper. Yes, by induction, but okay, what's the first step basically? It is going to be a recursive algorithm. The algorithm is not going to be as different as you might think. But there's one key thing we need to do. Yeah.
Moves have the optimal moves, and the current one is the best possible in the scenario that you're in. That is the optimal solution.
That's basically what we're going to do. But how? Maybe I'm being awkward. Yeah. We just need to update our recursive spec. Okay. I'm just going to update my recursive spec. I'm going to move from A to B with the minimum number of moves. None of the algorithm's going to change. Okay. And the proof of correctness basically won't change. The only slight addition is the following. So my goal is to move the top n rings from A to B, right? The only way to move this bottom ring from A to B is to get the top n minus 1 rings out of the way. The only way that's possible is to get it to C. So I know that any algorithm, whatever it does, eventually needs to somehow put the top n minus 1 onto C so that I can move the bottom one from A to B. And then it's going to have to move the n minus 1 back from C to B. That you have to do. Maybe there's other clever things you can do, but at the very least, you have to do that. And our algorithm is doing that. And by recursion, recursive spec is now saying it's doing it optimally, right? We know who we have to move the top n minus rings from n minus 1 rings from A to C. Our recursive spec says that's exactly what step A will do. We know we have to move the top bottom ring from A to B. Okay, we do that. And now we know we eventually have to move those n minus 1 rings back from C to B. And our recursive spec says it's going to do that optimally. So these 3 force moves, each of which we do optimally, and all we had to do was strengthen our recursive spec. The algorithm actually didn't change. We had the optimal algorithm all along, but now we can really justify it. Yeah. All right, any questions? Okay, good. Let's keep going. I have 2 more Thanks. All right, so that's it for Towers of Hanoi. Any more Towers of Hanoi questions? You have plenty of practice. All right, so the next one we're going to do is the greatest common divisor problem. Okay, so you have two big numbers, and you want to find the biggest number that divides both of them. Okay, so here are a couple mildly large numbers. Anyone want to guess their greatest common divisor? It's actually guessable. Yeah. 3? It's higher than 3. Yeah, it's 381. Okay. Yeah. Okay. So, does anyone want to propose an idea for an algorithm before I start giving away the answers? Yeah. Sorry, a little louder. Take the difference between x and y. Have x minus y. Okay.
And we can find, I think, we can find the greatest common factor between x minus y and y.
Yeah, so I think that's exactly what we have. So apparently this goes back to Euclid. So let's say that x is always bigger than y. Then some number q divides x and y if and only if it divides y and x minus y. Right? If q divides y, then subtracting y is okay. I wanted to make sure x greater than equal y so that everything remains non-negative. Okay. All right. So let's turn this into a recursive algorithm. Again, we start with some kind of sentence. I gave us a name, GCD, for greatest common divisor. Who wants to give me some variables and a sentence? Yeah, that's totally fine. Name the numbers for me. Give me some. Okay, x and y. Thank you. All right. So maybe given x, y, it's a little bit easier if I specify x to be bigger than y in terms of writing the code. Return. What did you say again? Yeah, the GCD of x and y. I mean, half of these recursive, or most of these recursive specs are like not super interesting, but they do a lot of work for us. Okay. And I'm assuming we all agree on the definition of greatest common divisor. Okay, so that's a recursive spec. Oh, well, does anyone want to implement it? Based on Euclid's amazing observation? Yeah.
You would take the q would equal difference x and y, and then you would basically just call CP again. Well, whichever one is the highest, x and the lowest.
Okay, so I think at a high level, you want to do something that's kind of like this. Y, x minus y. The only thing is I'm picky about the first argument being bigger. So maybe I'll write x prime is the maximum of y and x minus y, and y prime is the minimum of the two. And something like this. Oh, sorry. X prime, y prime. So all this is just swapping the two arguments to make sure the first one is bigger. Okay. We're missing one thing. Yeah. X what? Oh, we will do that in a moment. That'll be this. Yeah. Yes. We need some base case. What's a reasonable base case?
When x equals 0, return.
Okay, so if x is equal to 0, return what? Guess you turn y? How is it? Okay. Something like this. Okay, let's see what I had. I did if y is equal to 0, then return x. But okay. All right, so that's a simple recursive algorithm. Yeah.
X is equal to 0. That implies that y is also less than or equal to 0. What? Actually, for the rate.
Okay, so let's stick with this algorithm. Suppose x was I see. Oh no, suppose x was 10 and y is 0. What would the algorithm do? The one we wrote. Sorry? So okay, if x was 10 and y was 0, then x minus y would be 10, y would be 0 again. So we just end up calling 10, 0, 10, 0, 10, 0, 10, 0, 10, 0. So actually the base case of x equals 0, or no. Did I get that mixed up? Oh, does that mean my code is wrong? Maybe that means my code is wrong. What did I just say? 10 is 0. Okay, so maybe this is better then. Now I'm confused. Yeah.
Does the different way, it does a max of x minus y, capital Y.
Oh, I'm sorry. That's right. Okay. So this code would get stuck, right? This code would infinite loop. Okay, I'm not too confused. But this version here, which will catch y equals 0 as a base case, will just return x right away. Okay, good. Otherwise, I've been teaching this wrong for 5 years. Okay. All right, so sometimes you want to be a little bit careful about your base case. It is true that checking for x equals 0, you could get stuck. Y equals 0 actually will be okay. All right, so good. How might we prove correctness? I want to prove this algorithm is correct. Yeah.
We need to show that if C is like the greatest common factor between x and y, A shows also the greatest common factor.
Let's take Euclid's observation for granted. Suppose I'm okay with the fact that if q divides x and y, then it's going to divide x and y and x minus y. So we'll take that algebraic part for granted, but now we still want to show that the algorithm returns the greatest common divisor. So we're trying to prove the algorithm's correct, not that Euclid's correct. You better be correct. Yeah. A little louder. Another proof by induction. Induction on what? Proof by induction on the GCD. Did I hear that correctly? Okay. So how would we proceed? Okay, so I'm given some x and y. Now, if I look at the recursive calls here, the whole point of Euclid's observation is that the GCD shouldn't change, right? If I subtract out y from x. So, because we want to return the GCD of the original argument. So for us, actually, the GCD doesn't go down in our recursive calls. It stays the same because we want the subcalls to actually have the same value. So this won't quite work because our algorithm does not decrease the GCD of its arguments. We need something else to do induction on. Can we do it on y? Does y always go down? So let's say that x is 10 and y is 2. Then the subcall is going to do x is 8 and y is 2. Then just do it on x. Does x always go down? Well, what if x and y are the same? And you go like 5, 5, and then 5, 0. Could you do on x minus y? I have to think another. Does that work? Does x minus y work? Does x minus y always go down?
If you make your base case to be when x equals y, which is what causes y to go x to stay still, y to go 0, then technically all the x always goes down and you stop the base case when it wouldn't.
Okay, can we do something on if x is equal to y? Yeah, could I have added that base case? I think so, and then we do things differently. Yeah. You are correct. Unfortunately, I think it's written in ink up there. So suppose we're just doing this algorithm. You're all really close. Yeah.
Just do it on the max of like x minus y,
The max. Well, again, I think if you have 5, 5, and then you get 5, 0, the max stays the same. You've done the difference, you've done x, you've done y, you've done max. X plus y. X plus y will at least always go down without having to think very hard. Yeah? Okay. So we can do a proof by induction on x plus y, right? So, Euclid already implies that the GCD of xy is equal to the GCD of x minus y and y, where you might swap them around based on which one's bigger. Okay. Do you maybe I should put this in quotes. Okay, so if I put it in quotes, this is just sort of mathematically, and if I don't put it in quotes, I'm talking about our algorithm. Okay. And our algorithm by induction on x plus y tells us that our algorithm, when I call GCD, I'm not going to write the max min stuff, x minus y, I will really get the mathematical GCD of x minus y and y. Hopefully that notation makes some sense. And then Euclid will tell us that this is the mathematical GCD of x and y. Yeah, I've kind of skipped the base case, but we're all friends. Okay, is that okay? But the real key point is that, okay, so, Euclid's simple observation tells us that, subtracting y is okay. That's still going to preserve the GCD. Okay, and then recursion tells us that our algorithm, when I call it on x minus y and y, I will get the true GCD of x minus y and y, which is mathematically equal to the GCD of x and y. Okay, recursion here is valid because the sum of the two parameters is always going down. Okay. And it bottoms out. Okay. So that's so much for correctness. What is the running time of our algorithm? Yeah. Is it x divided by y? Okay, so what would be like the worst case? Okay, so let's see what I have written. Thought I had something written. Okay, so okay, each iteration is going to decrease the sum by at least 1, depending on how, because y is at least 1. Okay. So what's the worst number of iterations? Maybe something like x plus y. Maybe y is 2, y is 1. So, good. So this algorithm will be bounded above by x plus y because you know the sum is always going down by at least 1. Okay, so conservative analysis. Okay. Is this a good running time? It's not a good running time. Okay, so what's the issue? Is this a linear running time in its input? Okay, why? It looks kind of linear to say x plus y. So why doesn't it count as a linear running time? Maybe you've all done this before, so you're just staring at me? I don't know. Yeah. So it's linear because it's just a linear function of x and y? That would be a pro argument, right? Oh, yeah. Ah, okay. If we look at the bits, right? X and y take log x and log y bits respectively to write down, right? If x was 100, you only need 6 bits. If x was 1,000, you only need 10 bits. Okay. So this running time is actually exponential in the input size. Okay, so it's actually to some extent a terrible algorithm because I can give you huge number if I gave you, 1,000-bit numbers. Okay, it's not so hard for me to give you a 1,000-bit number, and your algorithm will just never terminate because it'll take 2 to the 1,000 time. All right, so what would be an example of a bad case? Any example is fine. Yeah, y is equal to 1, right? Then you have to start going 9 and then all the way down, something like this. Okay. All right. Yeah, that's more exciting than my example. Okay. So, I was gonna. Well, someone already suggested it anyway. All right. So our next goal then is to make a faster algorithm. Okay. So we're going to try to work off the observation on the right-hand side here, which was actually already suggested earlier. So before we we're just doing x and x minus y. And if you kind of imagine like in this example, you're just going to keep subtracting 2, subtracting 2, subtracting 2, subtracting 2. Why not just go all the way down to 101 mod 2 and then work from there? Right? You're just going to keep doing the subtraction over and over again. Let's just shortcut it by doing x mod y instead of x minus y. Okay, so it's the same algorithm, it's just skipping a bunch of the subtractions in between. Okay, so, okay, so if x is, 10y plus something that's smaller than y, some remainder, if r is that remainder, I know that q divides x and y if and only if q divides y and r. Okay, slightly more clever than Euclid's original observation. Okay, so let's work with that. Here then is sentence doesn't change, same recursive spec. The only difference in the algorithm is I'm now returning the GCD of y and x mod y. Actually, the code got cleaner because x mod y is always smaller than y, so I don't have to do this min-max nonsense. Okay. All right, so now how can we prove this? We're going to prove it by induction, but anyone want to nominate something to do induction on? This one's actually easier. Yeah. Oops. Yeah, we can do induction on y now, right? Because x mod y is always smaller than y because modulo is going to give you something smaller. Okay, so y is clearly going down. The GCD is preserved. Otherwise kind of same proof as before. I won't write it all the way out. Okay, so this is actually easier because it's easier to see that y always goes down. We don't need any of this x plus y cleverness. Okay, so I'm always replacing the y argument with something modulo y. That'll be smaller than y. So I can feel good about my recursive call as long as that second parameter keeps going down. The base case is y equals 0. All right. But the whole point of this exercise was the running time. Okay. So let's try to reanalyze the running time for this more aggressive algorithm. I'll skip the base case, that's clear. If y is equals 0, we're done. Okay. How can I try to justify we're making a lot of progress? This one. This one's always a little trickier. Does anyone want to give a try? Yeah. So I want to try to analyze the running time. Okay. The base case will just be a constant time, so that's not a big deal. I want to do better than x plus y. I do know y always goes down, so we have like an O of y running time, assuming that modulo takes constant time. Otherwise, it takes log x time or whatever to do some bit arithmetic. But I want to do better than O of y because that's still kind of exponential. Yeah.
Maybe like you can do like ky plus r. It's like take away the ky. Y is either going to be like greater than x over 2 or like less than x over 2.
Okay, great. So let's look at two cases. Y is bigger than x over 2 and or greater than equal, maybe we can put it over here. Y is less than equal to x over 2. Okay, so what's happening when y is bigger than x over 2? Yeah.
Well, r is going to be less than.
Okay, so then r is going to be less than equal to x over 2. Okay. So some level I'm replacing x with a number that's at most half the size. Okay, and what happens is y is at most x over 2. Yeah, that's right. So r is less than y, which is less than equal to x over 2. Okay. So intuitively, we're replacing x out of our two numbers with a number that's half the size. Okay. And what do you do induction on? So one way to think about it is like this. X and y are always flipping. I mean, y becomes x, and then you have an r, right? And that r is going to become x the next time. So you can think of this as also saying that every two iterations, x will go down by half. Because this first iteration, this r value will be x over 2. And the iteration after that, r will come back on the x side. So every two calls, I'll divide x by 2. Yeah. That also means the y side is always divided by 2 every two calls. That's one way to justify it. Okay, so then every two iterations, x goes down by half, y goes down by half. How many iterations do I need? Or how many recursive calls? Oh, do I have this written? I don't know why that's there. Okay. All right, so that'll imply something like log x plus log y. Every 2 recursive calls will half x. Every 2 recursive calls will half y. Okay. That's, of course, at most log x plus y, which might be more compact. It doesn't really matter at this point. All right, but now we at least have something that's actually linear in the input size, the actual number of bits you're given. Okay, that's if we're counting modulo as a constant time operation. Otherwise, it'll just take, log x, log y time to actually do long division or something. Okay. All right, any questions? Yeah.
Can you explain why we use them for simply size?
Why? Well, I think that's the why is because that's sort of how it's defined. You do really want to think about, because or you can also ask why the previous algorithm was just unsatisfactory, which is that I can give you, on a small USB, a 10,000 bit number, and your algorithm will never terminate, even though the input's very small. It can be written down very small. So it's sort of defined as, and it helps us distinguish between these two algorithms, right? It prompts us to ask for more. Question.
Just like, isn't log x plus log y log x times y?
Yeah, they're all kind of equivalent up to a constant. Yeah. Anything else? Yeah.
Do you just like summarize the slide as a whole? Really quickly?
Yeah, I can summarize the slide. So before this, we had first done maybe the first greatest common divisor algorithm that came to mind, which was just gradually subtracting, subtracting, subtracting. We could prove correctness. Actually, it's a little bit trickier because you have to do x plus y, but you can prove correctness because x plus y was always going down. But the running time sort of took time proportional to x plus y, which we don't really count as linear time because x and y can be represented in logarithmic that size. So we wanted a faster algorithm. And the observation, which actually was already previously suggested earlier, was, the worst case is like when x is really big, y is really small, and you just keep subtracting y. So why not just do modulo? That's what we're doing here. We're doing the modulo algorithm. And now the running time analysis was a little bit more slick or a little more clever, but we're also trying to get a better running time. So maybe that's appropriate. But what we showed is that we have two cases. One is where y, the second argument, the smaller of the two, is at least x over 2. Then x mod y will give you some remainder that's at most x over 2, right? Just because it has to be in that difference, x minus y. Or if y is at most x over 2, I know the remainder is at most y because it's modulo y, and that's at most x over 2. Okay. And in our recursive call, r is going to go here, right? So I'm replacing x and y with y and r. And r is at most half of x. Okay, so one of my numbers is getting cut by half. If you think about it as like counting the bits, I'm kind of getting rid of 1 bit each time. And that's what we really want. We want to make progress in terms of bits, not just the actual quantity being represented. That's one way to look at it. Yeah. Well, yeah, counting down the bits does count down to reduce the quantity. Of course, that's true. But before, when we said, I reduce x plus y by 1, I wasn't really making much progress on the level of bits, and that's how I ended up with this exponential running time in truth. Yeah. Yeah.
So then, could you say that anything that is just O of n is just exponential because you can represent it in bits?
Well, so there's going to be lots of differences, and in general, we won't be too picky. I mean, there'll be other problems where there's numbers floating around. We just assume you can add and subtract in constant time and won't make too big a deal about this. Now, if you're given n numbers in your input, then you have n different things. If you're given the number n in your input, that only takes log n bits. But if you're given n different inputs or n different things, they might themselves be numbers requiring some number of bits. But the dominant thing is the n different things. These are good questions. Yeah, this sort of thing won't come up that much, except it will come up critically after the first midterm, or maybe the lecture before, but not on the first midterm. Okay, but it is good to keep the when numbers come up, especially when the input is just a number, two numbers, a constant number of numbers, to think about what is the actual representation size. Okay. And for a sorting problem, that's not such a big deal. The real issue is the fact that you have n different numbers. Okay. All right, so that's so much for GCD. Okay, so I wanted to give in the remaining time one more example of something we can prove by induction. Again, it's not going to be so algorithmic. Like I don't think this will be algorithmic at all, but it'll be fun because it'll be on graphs. So you've all been exposed to graphs to some extent before. Maybe you had to like implement BFS and DFS and things like this. Okay, so graphs, we have these dots, these vertices. We have edges connecting between them. Graphs can be directed if they, you can only go from A to B, or undirected is kind of like both directions or a mutual relationship. Of course, you know what graphs are, you know what the internet is, you know what social networks are. So here is a particular kind of graph, which of course you know is a bipartite graph. So here I'm able to split the two vertices into two sets, and every edge has one endpoint in one and one endpoint in the other. A side, B side, left side, right side. Okay? And we're going to look at two problems on a bipartite graph and understand the relationship. The first one is called a matching. So your goal is to try to take as many of these edges as possible so that the endpoints are distinct. So you can only take one of the edges incident to this vertex, one of the edges incident to that vertex, and so forth. Okay? And so, these edges can clash with each other. So it's non-trivial to try to get the maximum number. All right, to make sure we're on the same page, what's the best matching you can find? In a minute. Yeah.
Exactly what it is, but like the max number of edges you could get would probably be 6 items.
Okay.
People will use each like pair of vertices at once.
Okay, so 6 is an upper bound just because there's only 6 vertices on one side. Anyone figure out how to get 6? Right, because each edge will have to use up, say, one of the vertices on the left. So that already upper bounds. You can do at most 6. Anyone find 6? Anyone find 5? Yeah.
Okay, so the bottom two are basically divided.
I'll point and you tell me whether to take that edge. Should I take this edge? Okay, so that'll eliminate this one, this one, this one, this one. How about this edge? All right. That eliminates this one and this one. And so our next possible edge, how about this one? We'll take this one. Okay. So that will give you, I guess that is slightly different. That would be an example of a matching of size 5. Okay, 5 edges. They don't share any endpoints. And at the moment, I don't know if you can get 6. Okay. All right, but at least the definition makes sense. Sorry, I have to go a little quickly here. Now let me give you another problem. So this is called vertex cover. Okay. This is called vertex cover. The goal is to take the minimum number of vertices, so you're taking at least one endpoint from every edge. So you want to take as few as possible. Okay. So for this edge, you have to take at least one of the two. For this next edge, you have to take at least one of the two. But you're hoping, you could take a few vertices that cover a lot. So 6 is always possible. You can always take just one side. Anyone do better? Yeah. 2? Okay, which 2? This 2? Okay, so that means like this edge you're not taking any vertex incident to it. I mean, you have to take at least one of those two endpoints. So you want to make sure that for every edge, you have one of the two endpoints. So you can do 6 because you can take everything on one side or the other. Can anyone beat 6 in -1 minute? 5. Okay, so you can get 5. Okay, so I'm going to make this slightly less rhetorical just to try to cram this in. Now, these are actually what are called dual problems. So imagine you're like packing a suitcase or something, right? The left side problem, you're trying to take as many edges as you can, subject to these constraints on the endpoints. The right side is sort of the opposite. You're trying to take vertices that cover all the edges, right? So it's sort of the constraints in one become what you're taking in the other, right? The vertices represent constraints in the first problem, and then they're what you're taking in the second. What you're taking in the second problem, the vertices become the constraints. Or did I get it back? No, the constraints in the second problem, the edges, become what you're taking in the first problem, right? The edges are saying you have to take at least one for every edge. So they're called dual packing and covering problems. So I claim that for any matching and any vertex cover, there needs to be at least as many vertices as there are edges. Why? I'm not gonna say that. Yeah. So of course the matchings, of course, each represent some requirements, right? But they have disjoint endpoints. So you have to take at least one endpoint from every edge, and there's no overlap there. So you have 5 edges in your matching, you need at least 5 in your vertex cover just to cover that matching. Okay, so that's weak duality. One direction is always easy. The next direction I'm just going to cram in real quick is a claim that they're actually equal for this problem. So weak duality is often true in these packing covering setups. Special cases, you can actually prove they're equal. Okay, and the one thing nice, if we look back before, we had a matching of size 5, a vertex cover size 5. They mutually certify each other to be optimal, right? Okay, so let me just give a sketch of the proof, and then if you're interested, then you can read the notes where there's also some pictures. Okay, so what I'm going to do is I'm going to do induction on the size of the graph, which is the number of vertices plus number of edges. Okay, if it's an empty graph, it's just 0 and 0. There's nothing to do. Okay, so in the general case, you have some graph. It's non-zero, non-empty. Okay, and I'm going to assume that the minimum vertex cover has size k, which has a certain set of vertices s on the left, a certain set of vertices t on the right. Okay, and our goal is to be able to produce a matching of size k, and we're going to do this really fast by induction. It's not supposed to be this fast, but we had a lot of fun doing Towers Hanoi. Okay, so I feel like it's going to lose the effect. That's okay. So we're going to break this down into two cases. In the first case, there's some minimum vertex cover, so it has to be optimal, that has vertices on both sides. In the second case, every minimum vertex cover has all its vertices on just one side. Okay? So the second case is sort of this extreme polar case. Now, in this first case, there is a minimum vertex cover with vertices on both sides. Okay? And we're going to break that down. Or we're going to try to get say in this example, matching a size 5. Okay? So what I'm going to do is this. I'm going to look at first the graph where I erase the vertex cover on one side. Okay, so I'm going to erase all these vertices and look at this remaining graph. And I'm going to do the opposite for this other side, okay? So I'm going to kind of break this graph into two. Notice they're like quite disjoint. Okay, so let's look at just one of these. All right, what are some observations? What do you notice about S in this graph? Please help me. It's a vertex cover. Okay, it's a vertex cover of this small graph. And this smaller graph is smaller because you deleted at least one vertex on the other side. So that gives you a matching of size 2. Just by induction, there's a matching of size 2. And we can, of course, do the same on the opposite side. Okay, T again will be a vertex. This is just completely symmetric. And so you're going to get a matching that matches this cover. Can I do it? Something like this. Okay. So in a case like this, you can decompose it and then you put it back together. If I went a little bit more slowly, then it's not hard to see that these are promised to be disjoint from each other by the way we kind of ripped out the parts of the graph. All right, so that's one case. But the point is that we kind of focus on one side or the other. That gets the graph smaller. We get the matchings by induction, put it back together. Okay. All right, let's do the remaining case. I promise we'll be done. So in the other case, everything's stuck on one side. And what we do then is we imagine dropping an edge. Just pick any edge and drop it. Okay. So say I drop that purple edge, and suppose T remains a minimum vertex cover, then what? If T remains a vertex cover, then by induction, then we'll get some matching, right? Something like this. Because I dropped an edge, it got smaller, it's still a minimum vertex cover. The only remaining case is what if T is not a minimum vertex cover? Okay. That means there's some smaller vertex cover, right? So in that case, it'll look like this or something. But if that was the case, I should be able to take this, something like this, and that would give me a minimum vertex cover for the original graph. So I would take the opposite endpoint of the edge I removed. Okay. So in that way, you know, I should be able to take the smaller vertex cover in that graph removing an edge, add one of the two endpoints of our removed edge, and get some vertex cover with something on both sides. But supposedly that didn't exist in this premise. Okay, so this scenario doesn't happen. Okay, I went a little bit fast, of course. But by those two cases, you'll prove this nice theorem that the maximum matching is equal to the minimum vertex cover in a bipartite graph. Okay, this will come up again later. It's called Koenig's theorem. Okay, sorry I'm over. That's it. Thank you.